not wrong. So we have today and tomorrow. So I will use this time to discuss a little bit of investigations in the very last part of our interest, which are the buildings and the subsoil. So maybe this will be relatively new, especially for the diploma students, but I don't know if already discuss similar aspects. But as I mentioned already last time, it's becoming more and more interesting also to consider when we are looking at hazard and in particular risk, to consider the effect also of the building structure on the level of shaking that can be recorded. I will I will start then these lectures using the material that Bojana Petrovic prepared some times ago, and I think it's quite good material. So I will make use of this. And so unfortunately, you didn't meet Bojana this time because of the COVID situation. So I'm giving the lecture. And okay, so we will start discussing a little bit about the methods for studying the building dynamic behavior and also the soil structure interaction effects. I see here a nice picture. This is taken from some of our past experiments in Central Asia. This is the capital of Kyrgyzstan, is Bishkek, and you see the mountains here when Tian Shan is starting, where also large large fault structure are existing that can generate large shaking, earthquakes with significant shaking like they have done in the past. And but you also see already here that this is one of the cases where new buildings are built in high hazard areas. So it's one of the examples that is telling us that we have to be careful in considering the right design for these structures in order not to have in future problems. So how we can study the building dynamic behavior? We can use, of course, real data analysis, like we are doing also for studying the underground structure, or we can rely, for example, on numerical modeling. But of course, numerical modeling requires a good estimation of the parameters that we can include in our simulation. The real data analysis can be based on either on ambient vibration measurements. So we already have seen something on the seismic noise measurements for the ground, but also for some structures. Can be based on weak or strong motion when available measurements. So if buildings are instrumented, so if sensors like those we are putting on the ground are also included or installed inside the buildings, they also can tell us something of the building behavior during shaking. Or also force vibration measurements can be done. So the building can be subject to different, we can have different kind of tests that are putting on a force vibration the building and having therefore also sensors on the building structure itself. We can also measure how the building is behaving. And for example, Chiara, who is following the course, has a quite a good experience in some kind of, let's say, induced vibration to the structure. Most of the analysis, also in this case, is based on the Fourier transform of the recorded signals. So here you see, for example, some spectra, Fourier spectra of recordings in two different directions made on the roof, so on the top of the buildings. And you can immediately see the resonance frequency of oscillation of the buildings in the two different directions. Or one can rely on modal analysis and frequency domain decomposition. So we can also take advantage of this analysis always based on recorded signal. Or if we want to also estimate how waves are propagating inside the structure and distinguish between, let's say, the part of propagation of waves in the structure and the part of its oscillations, so of its modal behavior, then we can also use the convolution approach. And we will see all of these procedure a little bit more into detail. So the modeling, for what regard the numerical modeling, many studies are based on finite element modeling of a structure. And of course, you can imagine that for doing a finite element modeling of a structure, we have to know it very well. So we have to know many details of a structure and of a characteristic of a material that is composing the structure itself. And very often we need to make some measurements directly in the structure, also to fix some of these parameters in order to improve the quality and the reliability of a numerical simulation. This kind of measurements inside the building structures, like the one you have seen before, can be done, for example, with permanent installation. So the number of buildings now, I would say, in the world that start to have instruments that are installed for a permanent time, okay, for the last duration and the life of a building is dramatically increasing. And these buildings are offering us the opportunity to measure, to estimate directly how the building is behaving during shaking. These are some examples of installations that we have done. If I remember correctly, that's the roof of a building in Istanbul. So we install here a accelerometer. So this was mainly a low-cost accelerometer, where you can see inside, it's a sort of small computer with a microcontroller, a MEMS for measuring the acceleration of a structure. Then the communication was made, since we had a network of instruments, also via Wi-Fi antenna. We had the GPS that we use, not really in this case for the position of the instruments, but mainly for having a good timing of our signal. And a GPS, of course, receiver that was providing the correct time. So this is one example with low-cost accelerometers that are becoming more and more used now in the engineering and seismological community. So you will find also in the market quite a large number of solutions for average to low-cost accelerometers. Of course, the quality is not the same of let's say, higher cost instruments, but due to the limited cost, they allow you to increase the number of sensors that you can deploy, so increase the number of measurements that one can take. Similar system here is also installed in another place of a structure, but connected to a standard seismometer. So this is the same system, but with a seismometer. So here we were recording the signal from the velocimeter here, and then was transmitted and digitized by this box. And here, in another case, is the similar system, but with a small 4.5 Hertz geophone with free component of motion. So especially for relatively small buildings where the resonance frequency of a structure is small, this could be also a quite reasonable solution. Other kind of instrumented buildings, we have now a growing number of buildings which are instrumented also here in Friuli Venezia Giulia. So in recent projects, we instrumented 30 buildings with instruments at their base and at the top. Again, in this case, we are using a sort of average cost accelerometer with free axial. You see, this is installed directly inside the structure, and here in one of the column of the main part of a structure inside this quite complicated to study building with respect to the previous ones. Generally, we are working also, this is important, quite high sampling rate, because especially if we are measuring acceleration, we are also interested in recording the high frequency part of the signal. And especially if we are looking at methods based on the convolution that are looking at the propagation of waves within the structure, due to the short time of propagation, we need also to have a very high sampling rate in order to catch the propagation of the waves inside the structure itself. Okay, generally in this case, you see the instruments can also be plugged directly to the internet or plugged to the power supply, and we always use also some extra power supplies in case of power back down, in order that in case of seismic events, the data are not lost. So these are for permanent measurements, but in some cases you can also rely on temporary installation. So we cannot wait for a long time to know how an earthquake, a building can behave during shaking. So what we can do is to make just rapid measurements inside buildings. And again, this can be done measuring the ambient vibration. So simply how the building is shaking during the small vibration that are exciting it, yeah, under normal, let's say, routinary condition every day due to the normal seismic noise that we have in the area. Here you have two different kind of stations. This is an old Mark sensor at 1 hertz that I use a lot, but it's not probably the most portable one because it's quite heavy, few kilos and quite big. This is an old EDL station. So you see the sensor is recording the motion in free component. The motion is transmitted, let's say, through the cable to the digitizer, and the digitizer is digitizing directly the signal. And here you have also a battery that is providing the necessary power supply to the seismological station. This is another kind of instrument, smaller, so it's a 4.5 hertz geophone connected directly to another kind of digitizers, much smaller and portable than this one. It was more recently done. So you have plenty of solution also for this kind of measurements that nowadays can be carried out quite in a simple way. So this is a very small instrument, and this you can carry without any problem in your hands, and the installation is very rapid. So you can install several instruments like this inside the buildings in a few hours. So of course you can also, oh sorry, another source can be not waiting for earthquakes, not waiting or not recording only seismic noise, because maybe the ambient vibration are too small also for our recorders, or because we want to check the behavior of a structure under special signals, or maybe signals which are related to the frequency of oscillation of our building. So in one of our experiments, we use also a Thumper track for generating seismic signal. We had many of these instruments, nearly 30, positioned in different places inside the building, and especially at different level. And when we started generating some signal with different frequencies, that was recorded, of course, by the sensor. So the Thumper track was, you will see it here, just nearby the building where we had the instrument. When you start working, you see something like this. So in this way, in this way, you have clearly a signal that you can control. So you know what is the frequency, you can control the amplitude, and therefore you know what to look at in your data. So you can also see how the buildings is changing its behavior under different frequency component.
Professor,
Yeah,
this truck is like a vibro size or?
yes, more or less, yes. Yes, you have this mass here, you see, and this was oscillating up and down like this,
Uh,
inducing quite a large signal. Generally, this is hardly going or reaching down to 1 hertz, so you don't reach it. So if you have very tall buildings, for example, with a very low frequency of vibration, probably you are not able with these instruments to excite the building at its own frequency of resonance. So generally, this could be better for higher frequencies structure. But anyway, it's good if you can combine also this kind of active source with a passive one. So by it's okay.
yeah, okay, okay, thank
So
you.
just in front of this, by the other part of the street, there was the building um, that we installed, and it's a building very similar to this one that you see on the slides, where we instrumented the structure with several buildings. We will see later some results of this experiment. Okay, so on what is the analysis based? You see
Hello,
again,
Professor.
yes,
In the previous slide, we have the kind of vibro size where we record the vibrations. So we have to record the vibrations from all directions of the building, or only one direction
good
is in.
question. Yes, I wanted to show you later,
Uh,
but you see, these are free component sensor. You see here,
yeah.
there is an arrow, no, on this sensor. So this arrow, generally in seismology, we would put it in the direction of north, no?
Mhm.
It's our north direction. And then you will have another horizontal component here and the vertical one. So we are measuring the translation of motion in free component. So, and of course, you see that there is the bubble that you have to uh, correctly install in order that the instrument is recording on the horizontal plane, the two horizontal component of motion. Here, we made some modification on the base. You see there is a plate, this is a metal plate, that we use just to have a good coupling of a sensor with the ground. So the weight is keeping the sensor just on the ground here, because this is just the floor of the building structure. So when we go in the building, doesn't matter. In this case, you see the north is quite well oriented with respect to the building, but can also happen that the north is somewhere in between for different azimuth.
Yeah.
So generally we define one direction along which we orient our sensor, and the other direction will be orthogonal to one. So we will have a sort of longitudinal direction in one of the two direction of a building, and the other one in the other direction of a building, okay, in the transverse direction. In order that when we analyze the recordings, we know that all the instruments were oriented in the direction where we also expect the major movement of the structure. Okay,
Okay. Thank you.
you're welcome. So, so you can record things, and as usual, then after recordings, we take our data, and most of analysis, as we know, is based on the Fourier spectrum. So GDT, again, we have seen it different times, is our signal, and so we transform the signal in the time domain simply in the signal in the frequency domain, so through its Fourier transform. Again, what is very important is to remember that the Fourier transform of the signal is a complex function with a real and an imaginary part. So in our analysis, we will not only consider the amplitude, so the modulus of this function, but we will use a lot also the information coming from the phase. And if you remember, the phase is nothing else that the arcotangent of the ratio between the imaginary and the real part. So we will make use of all the information that are provided by the Fourier transform of a recorded signal. So this is a really an important thing that you have to remember. So this is the building of before. So we were somewhere here, just in front in the square. You see here a small container. In this container, in reality, we install also an array of seismometers that were installed in a borehole here. So we drilled the borehole here. I showed you last time when we were discussing borehole analysis in Istanbul. So that's this place. We drilled boreholes. We installed the instruments also in the boreholes. The signal was going here in this container where we had the digitizer, and from here we were transmitting the data to a center. And also we installed instruments inside the buildings. With the green, you see these are permanent instruments that we installed here in some position inside the building. With blue, you have instruments like the one I showed you before, installed in each floor of the building and in different positions inside the building itself. So we had, as you can imagine, a quite large number of sensors for these experiments, more than 30 inside the structure. So then you can record the signal. That can be noise simply, or can be the signal generated by the Thumper track or by the vibrators, if you prefer, on the free component. And then you can start for the simultaneous windows of signal on the different stations. You can calculate the Fourier transform and then the spectral ratio with respect, for example, a reference site. What will be the reference site in our case for a building? In this case will be a sensor which is, for example, at the base of the building or just out of it, in order to reduce the effect of interference between the waves propagating inside the structure. So if you look at the signal that you record at different level, you take the Fourier spectrum and the spectral ratio, you will obtain results like this. So in red, you have one direction, and in blue is the other direction of motion. And you see the Fourier spectra, the spectral are plotted as a function of the height. So here you are on the floor, then first floor, second floor, and so on, up to the roof. So what is really clear is that you can immediately identify some peaks that are becoming, for example, here more and more important when you move up to the roof. You see, this is a very small frequency ranges, let's say from 0.5 to less than 2 Hertz. So we are focusing on a very narrow part of the spectrum. And then here we focus on the larger part of the spectrum from 3 to 5 Hertz. What is the difference from the low frequency peak and the high frequency peak? You see immediately that the low frequency peak is increasing continuously, going up to the roof. The higher frequency peak, they first increase, reach a maximum, then decrease. So at a certain floor, they are becoming nearly zero, and then they increase again. This is because these peaks of these frequencies are indicating different modes of vibration of the building, and in particular, the first and the second mode of vibration. So this you can see it very clearly here. In the
Professor,
first, yes?
I don't understand the blue curve. What
It's
does
another
it
direction, are the two directions of the structure. As I mentioned before, we are measuring in the X and in the epsilon direction, okay, on the horizontal plane. So we
Okay,
will
okay,
have an oscillation in this direction, and we will look at the oscillation in this direction too. And
okay,
you see,
okay.
since the building is not squared, there's a different stiffness in different direction, the two frequencies are not identical. So it means that the oscillation of the building is different in terms of frequency or period in the x direction with respect to the epsilon direction. Okay?
Okay, okay, thank you.
So it means we identify the first mode of vibration of a building in the two direction. And the first mode generally has exactly this shape, where you see that the oscillation of a structure is increasing from the bottom to the top. Clear? It's just moving
Yes,
like this, okay?
yes.
If we look at the second mode of vibration, then the second mode has a shape which is similar to this. So it's 1/3 of the wavelength of the first mode. So you see that the amplitude of shaking will increase, you see, at a certain level within the structure, then will decrease till when we have a node, which is more or less in this 13, 12 floor in the structure in both direction, and then will increase again in terms of absolute amplitude in the topmost floors. Okay? So
Uh,
simply in this way, yeah, tell me.
a question. I mean, we what cause which one of the mode will appear? I mean, what is the criteria for the second or for the first mode? It's the amplitude of shaking, no? Or
I mean, you will have both modes in the structure.
okay,
Of course, what can happen? Um, Generally, we always suspect that the first mode is the one where we have more, let's say, shaking, let's say. But for example, in my experience, in cases where we had shots, for example, close to buildings, due to bombs of the Second World War that had to be, let's say, exploded because they are still found in Europe. This is exciting mainly high frequency energy. In that cases, uh, since the spectrum of the original signal was more rich in the high frequency, in that case was exciting more the second or the third mode of a structure more than the fundamental one because it was closer. But in general, if you imagine a sort of wide spectrum, let's say exciting your structure, you will have all the modes playing a role with different amplitude. Okay?
okay, okay, okay. Thank you.
So this is another kind of structure where we made measurements. It's a little bit more complicated, you see, from the plant. And we could install at 13 levels instruments in different positions that you see here, indicated as A, B, and C inside the building. Of course, we would like to install always where it's the best for taking measurements, but very often we cannot place the sensors where it would be maybe more appropriated. In this case, the building was still in construction, but still we had to respect some requirement from the constructor for what regarded the installation. So in this case, you see things can be a little bit more complicated. So again, you have two directional motions and three different bands. I just put them separated in order to have some zoom on the different peaks. You see that again, we can observe some shaking increasing in the first band, both for the east-west and the north-south component. even if we have more complicated peaks, probably due to the contribution also internal part of the structure. In the higher frequency range, here we are 3 to 5 Hertz, again, we can recognize quite well the existence of a second mode, see, increasing, decreasing again, and so on. And then here, probably we identify in even higher frequency range, a higher mode, so a third mode of vibration of the structure. But you see that things can become more complicated depending on the characteristic of the building itself. This is another example of an experiment that we have found made here. It's a very complicated structure. It's a dormitory of the University of Udine in Gemona. And this area, you know, Gemona was strongly devastated by the earthquake that happened in 1976. This has been rebuilt after the earthquake. If I'm not wrong, this area was a church. You still see some remains of the old church. And some part of the building is also some refilled material. So this is complicating the analysis of the behavior of the structure, simply looking at the spectra quite a lot. So we made some installation in different parts of the building to try to understand, at least if we could identify the frequencies of resonance of the structure. You see, this is on the plan, that the building is quite complicated as this sort of U shape. You see from the blue curve coming here and so on. This is a sort of U shape. We could place the buildings in these different parts of a structure that are nearly linked by joints. And we made measurements in all these different parts, and we compare the recordings and the spectra for the different components. So different colors are the different component spectra for each station. So in blue is the north-south direction, in red is the east-west, and the black is the Z component that you see is nearly not showing any clear remarkable peak. So what is interesting to notice is that already at nearby sensors, you can immediately see some differences. For example, if you look at the spectra here, which is a 1A, and this spectrum here for the two different components, you immediately see how at a short distance between the sensor, the behavior of this part of the structure and this behavior can be significantly different. And this is shown clearly by the differences in the spectra for the different components. So this is, if you see in front, and you can also imagine how, or check how also the behavior is different from this side of the central part of the building with respect to the right side of the structure. So some differences are quite obvious. So this is a standard analysis that is done, and this is just a continuation of analysis that is showing how complicated, even for structure that apparently might look similar, how the results can indicate clearly a non-homogeneous dynamic behavior of a structure, even under these small vibration that are simply the ambient vibration. Another building where we made important estimation is a building of a university, the AHEPA hospital in Thessaloniki. I think Chiara knows this quite well. There we installed in the past a network for a long-term recording of acceleration during past earthquakes, but we made also some experiments to study the structural behavior of a building under vibration. And you see in this part of a structure of a hospital, there is a structural joint, and we wanted also to check how the building was behaving, maybe also considering the underground structure existing in Thessaloniki or very locally there. One important parameter that these long-term measurements, at least if you leave the sensors running, can provide you, is also if the spectrum is changing its shape, or if its main frequency of oscillation of the building is changing with time. So this is very important because, as we said, we consider that the frequency that we observe from the peaks we have seen before is related to the fundamental resonance frequency of a building. In reality, maybe the frequency we are measuring, if we don't make a spectral ratio, but if we look only at the spectra, so we look only at the peak in the spectra, is not only related to the oscillation of the building, but it's also related to the coupling of the building with the soil. So we are coupling the frequency of the building with the frequency of the soil. Since the characteristic both of the building and of the soil can change in time, it can happen that also there is some variability over time of the frequencies that we are measuring. You have to know that a change in the frequency of oscillation of a building is very often considered as related to a damage to the structure. So if my building will be damaged by the earthquake, it will change its frequency of oscillation. So it's very important also to know what is the original frequency of a structure, because if after an earthquake then we see it is changed, then we can have information if the building was or not damaged. And in some cases, you see, this change is quite obvious. And if you compare it, this is nearly, let's say, it's a little bit less than 1 year of recording and of measurements of seismic noise and the frequency that we were measuring during the day. I would say that there is a clear, for example, seasonal variability of the fundamental resonance frequency of the structure. So you see in more than 1 year, there is a clear cycle that is repeating. So with an increase of frequency end of summer and a sort of decrease, let's say, in winter. Of course, this variation is not very large. So we are moving from, let's say, 1.72 or something like this in summer to 1.68 or 67 in winter. So generally, we have a larger variation induced by significant damage to the structure, but still it's something that we can account for and might be related, for example, to changes in the characteristic of the ground in terms of water content or temperature changes affecting the behavior of the building, or that can generate some changes in the mechanical parameters of the structure. So this is something that we can also monitor simply with recording seismic noise and looking at the variability of the frequency of the structure itself. So I mentioned before a first mode of oscillation that we have seen as this shape with increasing with height. We mentioned the second mode, which has a node at a certain level within the building. And then we can have also a third mode and so on, depending on the kind of building structure. And sometimes this is also quite recognizable, as we have seen before. But what we are measuring, probably coming to one of the questions before, is just the combination of the different modes that are observed in our structure. And therefore, from the signal, what we try to separate. So we start measuring something on the structure that is giving in the different position, shaking like this, and we try to separate the different contribution using the spectral analysis or other analysis that we have seen before. An important mode that we didn't mention is also the component of rotational mode. So especially during earthquake shaking, we know that the building is not only undergoing, but also the ground. This you will have it also in seismology. Also in seismology, the ground is not only moving in a translational way, but there are also significant rotation of the ground. But our standard instruments on this single instruments can have problems in identifying this rotation of motion. But now, either combining the recordings of different instruments or using a particular, let's say, instruments like a gyroscope, it's possible not only to estimate the rotational modes, the translational modes, but also the rotational modes. This can be, it's done, as I mentioned, for the buildings, but also more and more even in seismological studies. So what is happening here is that you see our building, or our, can be also a piece of ground or underground, is subject to a rotation, and therefore there is a particular deformation of the structure and a rotation of a structure that is measured by our sensor. And we would like also, of course, to retrieve information about rotation, because rotation can be also important in terms of damage. So how can we use rotational modes? So these are just the typical example is we can make use of translational sensors. So our standard sensor measuring a translational motion in the north, in the X, in this case, or Y direction, where X in this case again is corresponds to the north-south direction. We take our recordings, simultaneous recording. Again, we calculate our spectra. And we can do it for two stations which are located at two different corners on the diagonal of the building. So these are the spectra for station 903 in the low frequency part, and these are the spectra for station 903 in a frequency range of between 3 and 6 Hertz. Again, I splitted the spectra in two windows just to improve, let's say, the visualization. The same are the spectra for the different component for the station 809. Black is generally the recording on the Z component that you see is not showing significant amplitude or peaks. So now what is happening? If this is my motion recorded, you see at my station, if I will have a movement in this way, I can have a movement in this way or in this direction. So in the two translational direction. So since my sensors are recording simultaneously the motion, in the case of translation, if I sum up the seismogram recorded at the same time, so I select the time that has to be coincide for the X component or for the Y component, I will improve the knowledge of a translational component. If since all the building is moving simultaneously in one direction. If I will subtract on the east-west component of a station, the east-west component of the other station, and the same for the north-south, the translational component will be cancelled. So in this way, I can cancel the translational component. What's happened for the rotation? For the rotation, something different happened. So if I sum up the two components due to the rotation, then I will remove the rotational component. If I make the difference between the components, I will enhance the signal related to the rotational components. So the sum is canceling the rotational effect and is enhancing the translational effect. The subtraction is canceling the translational effect and is enhancing the rotational effect. So if I do this, I can sum up my seismogram, or I can subtract them for each component, and then I calculate the Fourier transform. I can immediately identify the peaks in my spectrum related to translation and rotation. And that's seen here. So these are the spectra that we have seen before. Then what I'm doing, I just sum up for the north-south and the east-west component, or X or Y component, doesn't matter, the two signal, and then I calculate the Fourier transform. Or I subtract the north-south component at station 03 with the north-south component at 09, and I do the same for the east-west one, and I calculate the Fourier spectrum of the differences between the two components. What you observe is that you identify now in the sum two clear peaks, one corresponding to one direction and one to the second direction. And this peak is corresponding to the first mode of vibration in the two orthogonal directions. From the difference, now I clearly see a peak which is just in between, that has the same amplitude and is occurring at the same frequency on the two horizontal directions, which is related to the rotational motion. So it's quite obvious. In one direction, since the shape of the building is rectangular, I will have a different frequency of oscillation in this and this direction. But the rotation will be the same on the two, will be on the same frequency, on the two horizontal direction. So this is for, let's say, the low frequency band of my spectrum. If I repeat the exercise for frequencies higher than 3 Hertz, again, I can identify then a second translational motion for the X and the Y component, and a second rotational motion for the two, using the two component. Again, same frequency on the two component and same amplitude. So I would say we have a first mode in the X direction, then we have a rotational mode, then we have a first mode in the Y direction, if I go up in frequency, then the second mode in the X direction, a second rotational mode, and then a second mode in the Y direction. So just using two sensors, I was able then to estimate the frequency of oscillation, both translational and rotational, of the building itself.
Hello, Professor.
Yes.
From the previous slide, I have some confusion regarding, are you using the I mean, using a single source, but the both range of frequency are using, I mean, first from 0.5 to 2 hertz frequency, then again.
No, it's a wide spectrum.
Yeah.
And simply I'm visualizing, because if I put all together, you know, the first two peaks will be very close. I simply, from this window, I just make a zoom in the first 0.5 to hertz. And then I make a second zoom between 3 and 6 hertz. But the
Okay.
original signal can be an earthquake, can be also, for example, seismic noise, no? Recorded at two different sensors. This is from the plan, no? We are looking at the instruments from above. You can see it like this.
Okay, and the other question is related to the surface waves. Are we incorporating the fact like we have some different kind of motion if we use
Depends.
the body waves?
Surface waves, if a structure is small and they are long wavelengths, they can give you a sort of simultaneous behavior of a structure, no? All the structure is moving all together, no? Because generally they are much lower frequency than the dimension of a structure. So longer wavelength did this. Different if you have a comparable wavelengths with your structure that you're studying. So for example, if you have surface waves affecting a viaduct, no? Then you can have differential deformation on the viaduct or on a long bridge related to surface waves.
High frequency.
Sorry?
Sorry, so what's the product like with high frequency?
I didn't get it. Sorry, can you repeat? What do you mean with high frequency?
I mean, what's the product like with high frequency with the Roy model?
With ray model, I try to understand. So here we are not making the high, you're talking about the high frequency approximation and rays.
Dung, try to write your question in the chat.
Yes, maybe it's a good idea, sorry. Just explain me. If someone understood exactly the question, because I didn't get it correctly. Maybe sorry, I couldn't hear very well. So what I meant is anyway that, of course, the frequency content of the signal that you are analyzing, it's important with respect to the behavior of your structure.
Okay.
This will generate also the wavelength.
She said the black line with the high frequency, the black line in the right. Right.
Okay, here you mean?
Yeah.
This is the vertical component.
Vertical.
So it seems that in this high frequency part, you have some effect on the vertical component. One should understand that this is if there is some rocking on the structure or not, because of course you can have a rotation not only on the horizontal plane, but also in this way you can have tilting, right? So this could be some indicators of this kind of behavior, so that there is some tilting in the structure. Okay?
Thank you.
You're welcome. Sorry, I couldn't get it. So there are other way of estimating the building behavior, so not only using spectra. One of the most used methods now since nearly 20 years is what is called operational modal analysis, and one of the methods is the frequency domain decomposition. If you will work in this field, you will hear very often about FTD. So the method was developed exactly 20 years ago now, so 21st, yes. So, and So in principle, it consists in decomposing the signal after having calculated cross-power spectral density, and then you can decompose with singular value decomposition. No? And if you take from the singular value decomposition of the spectral matrix and you look at the autospectral density function, you will obtain information about a corresponding to a single degree of freedom of a single degree of freedom oscillator system. So you will obtain from the cross power spectral density, you decompose with SVD, and the information you have are relative to the mode, let's say, of oscillation of a structure. So these are some examples. This is a 9-story base isolated panel building in Bishkek, where we were working. We recorded in different positions of a structure ambient vibration, so seismic noise with stations, and then we applied this technique. And with this technique, knowing the position of the instruments were many and a little bit of a schematic shape of a structure, we identified mainly 4 different modes. The first mode, translation at 2.26 Hertz. A second mode quite close to it at 274. Then third mode at 855, and fourth mode at 9.65 Hertz. So let's see from this analysis what we could obtain. This is the shape of a first mode. If you look at from the top, so from above, here you will see how it will look like if you see from the epsilon direction. Here, if you see in front, so in the x direction, and that's just a perspective from like a bird view of a mode. So this is for the first mode that you will see is just giving you a shaking in this epsilon direction. And that's why in the epsilon direction, you see only the bending. And of course, if you see it, we can check it again. In X is something that is moving in front of you, so you don't see too much. You see, this is just moving simply in the epsilon direction, and this is the first mode of vibration of a structure. This is the second, sorry. Here you can see the second mode, that is a torsional mode. See how the torsion looks like from above and from below. You see it's happening very close to the base. So all the structure is mainly rotating from the top. And here you see even better the deformation of the structure. Of course, is exaggerated. You have to imagine this. So the scale is strongly exaggerated in the plane direction with a vertical one. Okay. And then here we have the second bending mode. So this time in the X direction. So we had the first bending in this part, then a torsion, and then a movement in this other direction. Oh, sorry. That we see now. Okay, now it's more clear. You see how it's bending also very well from the bottom right panel. So this is obtained with simple noise measurements and relatively simple analysis. And then we have a second torsional mode where we are also coupling a little bit of bending and torsion that you see here very well. So there is torsion, but also bending in the different direction that is giving this strange shape to the building itself. Okay. Then if you have more information on the structure, we come back to the structure that we have seen before, you can also attempt more, let's say, refine or fancy modeling of a structure. And generally, when you look at a finite element model, so the model should include information about the foundations, columns and shear walls that you can have here inside, or girders and slabs, so how they are designed, the principal internal and external masonry works, and the base. The model can also not include the reinforcement that in some cases can play a significant role, secondary separating walls, and additional roof elements. So it's quite a detailed model, but it's not including generally all the possible characteristic of a structure. And when you go in finite element model, you can have a very detailed, anyway, description of a structure. But as you can imagine, this is something that you can do for specific building. If you think to very large town, it would be impossible to make a numerical simulation for all the models, because simply building up the model could require a very long time. So these are some of the results of a finite element model when compared with real data, with the data coming from the analysis that we have seen before. So for example, we have DD, and you see that sometimes the results are not perfectly matching. There can be some difference in the frequency you are observing. And at least in my experience, numerical simulation always needs some, let's say, input from the measurements done in the field directly in the building to better constrain the model before the results of the numerical simulation can be, let's say, similar to what is, let's say, measured directly in the building itself. So if we come back to the building that we studied before in Istanbul, in this case, we identified the first torsional mode, the first bending mode in the X direction, and the first bending mode in the Y direction. The bad story is that the first torsional mode is appearing, and this is generally not certainly recommended in the design of a structure. This is one of a typical building called tunnel buildings that has been built in Turkey, but also in many other regions in Middle East and in Asia. So it's very interesting to study this kind of structures because are quite widespread in a large region. And the comparison of the results sometimes can be surprising because we could obtain values that in some cases are quite in a good agreement for what regard, for example, the translational mode, but can become quite different, for example, for the torsional modes. And this was related to the fact that the stiffness of the exteriors infill walls that is contributing to the torsional rigidity of the structure were neglected in the model. Only if you include also the exterior infill walls, then a better results, let's say, of the simulation. The results of the simulations were better fitting to the observation. So also something that generally might be considered not to contribute significantly, in reality was shown in this case to provide important information to have numerical simulation, but of course, good numerical simulation results, but of course, complicating quite a lot the numerical model and therefore requiring more information, things that, as I said before, not always we have. Okay, this is just if we want to study mainly how the building is moving all together. So what are his modal shape, what is his deformation and the ground motion. But more and more we are making use in the last years of what we call seismic interferometry. We have seen it already before last time for the soil, but you can apply exactly the same approach also for the buildings, or as we will see, where we have instruments in the ground and in the buildings, directly to study how the waves are propagating in the whole system that you are considering. One important point is that you can use as input signal earthquake recordings, which is especially for weak motion quite used nowadays, where recordings from long-term experiments are available, especially for short or temporary installation. You can use also ambient vibration measurements, or like in the case we have seen before, you can do the same game also with measurements by generated vibrations. Again, like we have discussed last time, mainly the idea comes from the Claerbout's conjecture, so that if we are cross-correlating noise traces recorded at two different locations, you can construct the wave field that would be recorded at a sensor if at one of the other locations there was a source. So the principle, I repeat it a little bit here. So just imagine we have a wave field generated by a source here at time 0, and two sensors in place A and XB. Of course, in the case of building, you can simply turn this image of my screen on the vertical direction. So you have an input of a wave coming below from the ground, and this is propagating up from the first floor to the last floor, okay? So what is happening? That my wave will reach at the time TA my sensor or my point in the position XA. And the same wave is propagating further and will reach the sensor in position XB at the time TB minus TA. So if I cross-correlate the signal, what I will obtain a pulse, the two signals, TB and TA, I will obtain a pulse that is located from the 0, and the 0 at this point, if I cross-correlate TB with TA, the signaling B with signaling A, I will obtain a signal that is the signal recorded, that will be recorded at station B if I was shooting at time 0, but in XA. So it doesn't matter what is happening before the signal is arriving in A. From the cross-correlation of convolution, I get the information starting from the moment when the signal is arriving A and it's propagating to B. And at the time 0, it's like if I have a signal that is generated directly in the position A. The same is valid if I invert the propagation of waves. This is typical with noise. For example, the source can be by both sides, so noise is coming by all the direction. And therefore, in this case, I will obtain the time reverse Green function. So since now the signal is first arriving in B, and then the signal is arriving in A, so my TB will be smaller than TA, but again, I use A as a reference, and therefore my time will become negative. I will have a TB minus TA prime, which will be negative, okay? So TB is smaller than TA, so TB minus TA will be negative and will be just symmetric to this one. So this is the acausal part that I will obtain, and this is the causal part of a signal. So why it's an advantage to do this? Because of course we never have signal which are spikes like this, especially when we record the noise. So if you look at two recordings at 2 stations of noise, you can see that there is some signal that is repeating that you can observe in the first and in the second station. For example, this signal here, this one here, and this one here. But you see, this signal is mixed with a lot of incoherent signal, quite difficult to recognize. So if I will cross-correlate, or as we see, we can also make the deconvolution, all the information of this signal that is always propagating, you see, from here to here, from here to here, from here to here, here to here, with the same time. So the time of the propagation from one station is always the same. All this information is simply compressed in the propagation of a single wavelet. And the time from here, 0, to the time of arrival of the wavelet correspond to the time of propagation of each one of this signal from one station to the other. So this is my green function. So I could add whatever source and convolve it with this green function, and I will obtain my seismogram. So this is the function that is describing the propagation of waves from one station to another station, okay? So if I cross-correlate all these complicated signal, I will obtain simply information about the propagation function, the function that is describing this time. And 0 here will be the time at which a signal generated from this station start, and this time that I can measure here is the time at which this signal is arriving to the other station that I use for the cross correlation. Okay? So we have to learn a little bit of wording, let's say. We already have seen it a little bit, and we have to distinguish a little bit between convolution, because we will see the deconvolution, the cross correlation, and the autocorrelation. So if these are two seismograms recorded at one station and the other station, the convolution can be described simply by this integral. If you remember from the Fourier transform property, we can calculate this integral not in the, let's say, in the time domain, but we can consider that the Fourier transform of the convolution will be equal to the product, so it's a simple product, of the Fourier transform of the signal at one station for the signal multiplied the signal at the second station. So how I can calculate the convolution? I just take the Fourier transform of the first signal, I take the Fourier transform of the second signal, and I multiply them. So I have then the Fourier transform of the convolution. If I want to go back in the time domain here, I can calculate the anti-Fourier transform, and I get it. In the correlation, this is the correlation function, but we have seen it also when we talk about the cross spectrum. The correlation is similar to the convolution, but it's just the product of the Fourier transform of the first signal for the complex conjugate. So if you remember, in this case, complex conjugate, it means we change the sign of imaginary part, the complex conjugate of the second signal. Okay? So again, it's quite simple to be calculated. How do they look like? And then for today, we can make a pause. Just imagine F is our square box signal. And then G is our time series, which is a triangular signal. Let's look at the convolution. So the convolution means, if you look at this equation, I have to start from a certain time 0, and then I calculate the sum of the two signals while I'm shifting them, okay? So here what I'm doing. Before my triangle, right, the triangle is somewhere here, so their value is nearly 0. At a certain point, the triangle start to reach the box and shifting it, you see, in this direction and shifting. At this point, from this point on, more I move to the right, let's say my triangle, the area calculated by the integral is growing. So for example, you see I'm moving toward the center and the area is growing and the value is increasing of my convolution function. At a certain point, I will reach the extreme end of the box signal, and it will be where I have the maximum of my function. From this moment on, my triangle starts to go out, so the integral is becoming smaller, so the amplitude is becoming smaller and smaller, and when the triangle is going out of the box, it will become 0. So this is my convolution function that I obtain convolving the two signals. If I have the cross correlation, I said my product is done inverting the, so using the complex conjugate of the signal. So it's for minus tau, and this you see it because G, it's flipped with respect to the original G. So what is happening now? That at a certain point here, the triangle starts to move inside the box. So my yellow area is increasing and is increasing until the triangle reach the diagonal, let's say, of the box. Here I will have my maximum. And then the area between the two functions, under the two functions, is diminishing until the triangle itself is going out. So you see that the convolution and the cross correlation are just functions that are mirrored in this way. Finally, simply the autocorrelation is the correlation of the signal with itself. Okay, in this case, it's quite clear. You will have a value that is increasing until it's reaching the maximum where the two signals are perfectly aligned, and then will decrease until when the other triangle will go out of this. What is the deconvolution? So we said that the convolution, which is here, can be calculated from the product of the two Fourier transform of the signal. So the deconvolution means I want to calculate the function giving the output of a system. So just imagine here, I know, for example, the recording here. I measure the recording here. I want to know the transfer function that is given the value of XA here is producing XB. So if I have a HDT is my seismogram on the roof of a building, and FDT, for example, is, or GDT is the seismogram at the bottom of the building, I need to calculate the transfer function, so the function that is describing the propagation of GDT through all the building to obtain the seismogram that I have at the top. So if we think to the convolution of before, if we transform everything in the Fourier transform, my transfer function, so the terms that is describing the propagation from the bottom to the top, is nothing else that the ratio between the Fourier transform of the recording on the top divided the Fourier transform of the recording on the bottom. Exactly like we have done with the spectral ratio. But here, please do not forget that we are not only looking at the modulus, we are using all the complex spectrum information. Okay? So if I want to calculate the function describing the propagation from the reference, that can be the recording at the bottom and the top of the building, I have just to divide the Fourier transform of the recording on the top divided the Fourier transform of the recording on the bottom. Generally, this is done in this way, or you can also use a sort of filter, a regularized deconvolution, because since you have a division, since the Fourier transform can have some numerical artifacts that are creating some large oscillation in the spectra, you need to regularize a bit the operation. Otherwise, where you have small numbers in the denominator, this spectral ratio will tend to explode. Okay? So we will continue tomorrow from here. Do you have any question on this? Oh. Still there?
Yes, yes.
Yes, we are
It's
here.
clear all?
Yes.
Okay, fantastic. So no other question for today? I mean, this principle is very similar if you do it in buildings, if you are doing it in soil, if you do it, say, for horizontal propagation of surface waves. So whatever it's called interferometer or something is based on this basic principle, okay? You can do it on georadar data, you can do it on nearly everything. Okay?
Okay, yeah.
Just think about it and we can discuss it if you like tomorrow.
Okay.
Great.
Okay,
Okay,
thank
then see you tomorrow then. Ah, I
Ciao.
see something.
I see you.
Ok, ciao ciao.
A domani.
A domani.
Thank you.
Thank you very
Professor.
much.
Goodbye.
See you tomorrow.
Ciao Maria Aurora.
Professor. Yeah, hello. Hey, Tarek.
Yeah,
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 hello?
yeah, yeah.
You have a class again,
Yes.
Oh, bro.
Okay, I'm coming to you. We have to talk, okay?
Okay.